quiet archive record. Tonight, we enter a space untouched by urgency, where time slows and thought softens. Let the edges of the day blur and quietly disappear. Europa is a bright, icy moon that circles Jupiter. It is a little smaller than Earth's moon, but it has become one of the top places to search for life beyond Earth. The reason is simple. Many scientists think Europa hides a global ocean of liquid water under its ice. If that ocean is real, and if it has the right chemicals and a steady energy source, it could support living microbes. The case is built from surface patterns, measurements of Jupiter's magnetic field near Europa, and models of how tides heat the moon from the inside. Tonight, we go through the case for life on Europa. Europa sits far from the warmth of the sun. At Jupiter's distance, sunlight is weak and the surface is extremely cold. The top of Europa is made of water ice, and it reflects a lot of light, so it stays cold. If Europa were just a frozen ball, it would be quiet and simple. But it is not. Europa's surface is cracked and reworked. It has long lines that cut across the ice, and wide areas where the ice looks broken into plates and shifted around. There are not many big impact craters compared to older moons nearby. These facts suggest the surface has been changed over and over. A surface does not stay fresh for free. Something has to drive change. On Europa, the main driver is Jupiter. Jupiter is so massive that it pulls hard on Europa. That pull changes as Europa moves in its orbit, and it also changes because Europa is tugged by other moons, especially Io and Ganymede. The result is that Europa is flexed. It is squeezed and stretched over and over. This repeated flexing makes heat inside the moon. This process is called tidal heating. Tidal heating is not just a theory made to fit the story. It is a known effect in the solar system. We see it clearly on Io, another moon of Jupiter. Io is the most volcanic body we know. Its heat comes from tides. Europa is farther out than Io, so it is not covered in volcanoes. But it can still be heated enough to keep water from freezing solid under the ice. If you want an ocean under ice, you need two things. You need water and you need heat. Water ice is obvious on Europa because we can see it and measure it. Heat is harder, but the tide story gives a steady source. The first hints of a hidden ocean came from the Voyager spacecraft in 1979. Voyager took images of Europa that showed a bright, smooth surface. Scientists saw long, dark cracks and very few craters. A surface with few craters is often young, because craters build up over time. So either Europa is younger than the rest of the solar system, which is not true, or its surface is being renewed. In the 1990s, the Galileo spacecraft flew past Europa many times. Galileo mapped the surface in better detail, but more important, it carried instruments that could sense Europa in other ways. One of these instruments was a magnetometer. It measured magnetic fields around the spacecraft. Jupiter has a strong magnetic field. As Europa moves through it, the field around Europa changes with time. If Europa has a layer that conducts electricity, a changing magnetic field will drive electrical currents in that layer. Those currents then create their own magnetic field. A spacecraft can detect that extra field. This is called an induced magnetic field. Galileo's data showed patterns consistent with an induced field at Europa. The best explanation is a salty, liquid ocean under the ice. Salt water conducts electricity well. Solid ice does not. A layer of salty slush might also conduct, but a global ocean fits the data and fits the surface signs. This is a key part of the case. It means the ocean idea is not just based on how the surface looks, it is supported by physics and measurement. The next question is how thick the ice is and how deep the ocean might be. The thickness matters for life because it affects how materials move between the surface and the ocean, and it affects how easy it is for energy and chemicals to flow. Some studies suggest the ice shell could be tens of kilometers thick in places. Other work suggests parts could be thinner, maybe only a few kilometers. The truth could be that the thickness varies. Europa may have regions where the ice is thick and stiff, and other regions where it is thin and active. We can learn about this from geology. Europa's surface has many kinds of features. There are long double ridges where two raised lines run side by side. There are bands where the ice looks pulled apart and filled in. There are roundish spots and jumbled areas called chaos terrain. Chaos terrain is especially interesting. It looks like the surface broke into pieces, shifted, and then froze back into place. On Earth, a similar look can happen when ice breaks and floats on water. On Europa, this has led to the idea that some chaos areas formed above warm ice, slushy pockets, or even shallow water. If warm ice or water can reach close to the surface, then surface material can also move down. This is important because Europa is in a harsh radiation environment. Jupiter's radiation belts are intense. High-energy particles slam into Europa's surface and break molecules apart. They can turn simple chemicals into other chemicals. They can also make strong oxidants, like peroxide compounds on the surface ice. Oxidants are interesting because they are chemical energy. If you bring oxidants into a dark ocean that has reduced chemicals from rocks, the reaction can release energy. Life can use that kind of energy. On Earth, many microbes live by using chemical reactions that move electrons from one chemical to another. Oxygen is a powerful oxidant on Earth. Europa might deliver other oxidants, so there is a possible energy cycle. Radiation makes oxidants at the surface. If the surface and the ocean exchange material, oxidants can be carried down. At the bottom, reactions with reduced material can release energy. This is one of the biggest reasons Europa is seen as promising. It may have more than one energy source. It has tidal heating to keep water liquid. It may have chemical gradients at the seafloor, and it may have surface-made oxidants that add extra chemical power. But this part of the case depends on transport. The key question is how much exchange happens between surface and ocean. If the ice shell is very thick and has little motion, then surface chemicals might never reach the ocean. In that case, the ocean could still have energy from rocks, but it would be more limited. Now we move deeper. If there is an ocean, what is under it? Most models say Europa has a rocky mantle and a metallic core. Europa has enough mass for heavier materials to sink during formation. This means rock should be present under the water. Water touching rock matters because it drives chemistry. On Earth, one of the most important reactions for deep sea life is serpentinization. This happens when water reacts with certain rocks and creates hydrogen gas. Hydrogen can be a fuel for microbes. Other reactions can produce methane and other simple molecules. If Europa has a rocky seafloor and some heat, it could have hydrothermal vents. Hydrothermal vents are places where hot water comes out of the crust. They can deliver minerals and create strong chemical gradients. On Earth, vents support rich ecosystems, even in total darkness. We do not know if Europa has vents. We have not seen them. But we have a clue from another icy moon, Enceladus, which orbits Saturn. Enceladus has a subsurface ocean and sends water into space through cracks near its south pole. The Cassini spacecraft flew through that spray and found salts and organic molecules. It also found tiny grains that suggest hot water reactions with rock. Enceladus is smaller than Europa, yet it shows that an icy moon can have water, rock, and active chemistry. Europa is larger and may have more tidal energy. This makes the idea of a working seafloor chemistry on Europa plausible. Still, plausible is not proven. The case for life should be stated in layers. First, Europa likely has a global ocean. Second, the ocean likely touches rock. Third, water rock chemistry likely produces energy and chemical gradients. Fourth, if there are building blocks and energy for long periods, microbes could live there. The first layer is strong. The second is strong but not directly measured. The third is reasonable, based on chemistry we know. The fourth is an open question. To talk about building blocks, we should talk about the main elements. Life on Earth uses carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, and many metals in smaller amounts. Water provides hydrogen and oxygen. Rock provides many elements. But what about carbon and nitrogen? Europa may receive some carbon from impacts. Comets and carbon-rich asteroids can deliver organics. Europa is also near Jupiter, and Jupiter has its own system of dust and particles. Over time, space can deliver useful compounds. There may also be carbon inside Europa from its formation. If Europa formed from a mix of rock and ice, it could include carbon compounds locked in, but the amount and form matter. Carbon could be in carbon dioxide, carbonates, or more complex organics. These choices matter for how easy it is for chemistry to build larger molecules. We can look for signs on the surface. Spectra of Europa show water ice, but also other materials. Some studies suggest salts like magnesium sulfate or sodium chloride. There are also hints of sulfur compounds, possibly from Io, which throws sulfur into space. There are also hints of carbon-based compounds in certain areas. The problem is that Europa's surface is processed by radiation. It can change chemistry and make the surface hard to interpret. What we see may not be a direct sample of the ocean. It may be a surface mix of ocean material, impact material, and radiation-made products. Even with that complexity, surface chemistry matters. It tells us what ingredients might be available. It also tells us what energy sources might exist if oxidants can reach the ocean. Next, we should discuss plumes. A plume is a jet of water vapor or icy particles that escapes into space. On Enceladus, plumes are clear and strong. On Europa, the evidence is weaker, but there have been hints. The Hubble Space Telescope has reported possible water vapor events near Europa. Some analysis of older spacecraft data has also suggested the possibility of a plume, but these events are not confirmed in the same way as Enceladus. If plumes exist, they are important for two reasons. First, they suggest that liquid or warm material can reach near the surface, which supports the idea of active transport. Second, they give a way to sample ocean material without drilling. A spacecraft could fly through a plume and capture particles. It could analyze their chemistry. It could search for organic molecules, salts, and possible biosignatures. Even if plumes are rare, it might be enough. You do not need a constant fountain. You need a few events that can be measured. But if plumes do not exist, Europa is still a strong target. The surface itself contains clues. The ice shell may move and cycle over time. Fresh cracks may expose material from below. Now we move to the idea of habitability. A habitable environment is not the same as a living environment. Habitable means it could support life, not that it does. What makes an environment habitable for microbes? Liquid water is the first. Energy is the second. The third is chemistry, meaning the right set of elements and compounds. The fourth is stability over time. Europa likely has liquid water. It likely has energy. Chemistry is uncertain but plausible. Stability is uncertain but could be long. Let's look at stability. Europa's orbit is influenced by resonances with other moons. These resonances help keep the orbit slightly stretched, which keeps tides active. If Europa were alone, tides might fade as the orbit becomes more circular, but the moon's system may keep the flexing going for a long time. That suggests the ocean could persist for billions of years, but we cannot be sure. The strength of tidal heating may change over time. The thickness of ice may change. The amount of heat may vary. Even so, a long-lived ocean is possible. Now think about life itself. If life began on Europa, it would have to start in darkness. It could not start like life on Earth that uses sunlight at the surface. It would likely start as chemistry powered by heat and rock, or powered by chemical gradients. Life on Earth may have started in warm, wet places with strong gradients, possibly near vents or in rock pores. If that is true, then a Europan seafloor could be a good place. But we do not know how easy it is for life to begin. It might be very hard. It might require many lucky steps. It might need special conditions. This is why Europa is so important. If we find life there, it would mean life began at least twice in one solar system. That would suggest life is common. If we do not find life, even in a strong candidate ocean, that would suggest life is rare or needs extra conditions. Either result is huge. Now we should talk about what evidence would count. One kind of evidence is organic molecules. Organic molecules are carbon-based compounds. Many are made without life, so the presence of organics alone is not enough. But the details matter. Life tends to select certain patterns. On Earth, living processes often create specific ratios of isotopes. Isotopes are forms of an element with different mass. For example, carbon has carbon-12 and carbon-13. Many biological processes favor lighter isotopes, so the carbon isotope ratio can carry information. Another clue is molecular patterns. Life often makes molecules with repeating structures or with certain handedness. Handedness is called chirality. Many biological molecules come in left and right forms, but life on Earth mostly uses one side for amino acids. That kind of strong preference can be a sign. Another clue is chemical imbalance. If you have chemicals that should react quickly, but they remain present together, it suggests a continuous source. On Earth, life is a continuous source for many imbalances. In an ocean, you might look for the presence of both oxidants and reduced chemicals in steady amounts, beyond what geology alone can maintain. But these measurements are hard. Now let's talk about missions. NASA is sending Europa Clipper. It is designed to orbit Jupiter and fly by Europa many times. It will carry cameras, spectrometers, a radar sounder, and other instruments. Radar can probe the ice shell. It can search for reflections from layers inside the ice and from the ocean below. It can estimate thickness in some regions. Cameras can map the surface in high detail. They can find young cracks and new surfaces. They can help choose future landing sites. Spectrometers can study the surface chemistry. They can map where salts and other compounds are. Other instruments can measure gravity. Gravity measurements can reveal how mass is distributed inside Europa. This can tell us about the ocean depth and the interior structure. A magnetometer can measure the induced field, again, with better tools. This can improve estimates of ocean salinity and depth. Europa Clipper is not built to detect life directly. It is built to test habitability and to guide future missions. There are also plans and ideas for landers. A lander could analyze surface ice for organics and other chemistry. However, radiation makes the surface tricky. The top layer of ice can be damaged and chemically changed. A lander might need to dig a little to reach less processed material. Even digging a few centimeters or tens of centimeters could help. A more difficult plan is to drill through the ice. That is far beyond current missions. Ice could be many kilometers thick, and the environment is harsh. But there are concepts. A heat probe could melt downward and carry instruments. It might take a long time, and it would require strong power. If a probe reached the ocean, it could release a small swimming device. That is the dream. Until then, we use indirect evidence. Now we step back. What are the main arguments that Europa is one of the best places for life? The strongest argument is that Europa likely has a huge ocean. Some models suggest the ocean could contain more water than Earth's oceans combined. That is because it is deep and global. A large ocean means lots of space for chemistry. It means long coastlines of ice-water contact. It means a huge seafloor area where rock meets water. The next argument is that Europa likely has a steady heat source from tides. Without heat, an ocean would freeze. The next argument is that Europa is not isolated. Its surface is active. That suggests motion. Motion suggests exchange. The next argument is that chemistry could be rich. Salts suggest dissolved minerals. Dissolved minerals are a sign that water has interacted with rock. The next argument is that oxidation chemistry at the surface could add energy if transported down. Each of these arguments has uncertainties, but together they form a strong case that Europa could support microbes. Now, to understand the case, it helps to compare Europa to other worlds. Mars is close and has a history of water, but today Mars is cold and dry at the surface. It might have salty water underground, but not a global ocean. Enceladus has an ocean and plumes, but it is much smaller. It has less total water. Titan has lakes of methane at the surface, and likely a water ocean deep inside. But the chemistry is more complex and colder. Europa stands out because it has liquid water in contact with rock, likely for a long time, and it is close enough to study. The next part of the case is physical constraints. If life exists, where would it live? The surface is the least likely place. Radiation is strong. The temperature is very low. Any cells on the surface would be damaged. Inside the ice shell, in pockets of brine, life could in theory exist. On Earth, there are microbes living in briny ice. But on Europa, the main hope is the ocean. In the ocean, life could be near the ice-water interface if chemicals are delivered from above. Or it could be near the seafloor, if hydrothermal chemistry is present. Near the seafloor might be best because that is where rock chemistry is strongest. But the ocean is dark, so life would be microbial. It would not have plants or large animals unless it had a strong energy supply and time. Even if life is only microbes, it is a major discovery. Now let's address the biggest objections. One objection is that Europa's ocean might be too cold. If it is near freezing, chemistry could be slow. But on Earth, life exists in cold oceans and in ice. Many microbes are adapted to cold. Another objection is that the ocean might be too salty or have the wrong pH. We do not know the exact composition, but Earth microbes can live in many pH ranges and salt levels. There are limits, but the range is wide. Another objection is lack of nutrients. A sealed ocean might run out of key elements. This is possible, but if the sea floor is active, rock can provide many nutrients. Also, if the ice shell cycles, surface material can supply more. Another objection is that radiation could destroy organics before they reach the ocean. That is true at the surface. But deeper in the ice, radiation drops. If transport is fast enough or deep enough, some compounds could survive. Another objection is that life might not start in the first place. This is the real unknown. We cannot solve it by logic alone. We need data. So how do we test the case? First, confirm the ocean and its salinity. Second, measure the ice shell thickness and find thin areas. Third, map surface chemistry and look for signs of ocean material. Fourth, search for plumes. Fifth, pick the best places for a lander. Sixth, sample material and look for strong biosignatures. Europa Clipper will cover several of these steps. Now let's go deeper into what we mean by biosignatures. A biosignature is a sign that suggests life. It is not a guarantee. It is a clue. One biosignature could be certain amino acids in patterns that are hard to make by chance. Another could be certain lipids, which are fats that make cell membranes. Another could be certain repeating polymers. Another could be a mixture of gases or dissolved chemicals that is far from balance. In a plume, we might measure the presence of methane, hydrogen, carbon dioxide, and other chemicals, and see if their ratios match biological processes. But biology can mimic geology, and geology can mimic biology. So we would need multiple lines of evidence. Now consider the ocean itself. If Europa has a global ocean, it might have currents. It might have layers of different temperature and salinity. It might have ice forming and melting at the top. It might have sediments on the bottom. All of these things matter for life. Currents can move nutrients. Ice forming can concentrate salts. Sediments can store chemicals. On Earth, the ocean is not a uniform pool. It is a complex system. Europa could be complex too. We should also consider how Europa formed. Europa likely formed in the early solar system, from a mix of rock and ice. It probably heated during formation from impacts and from radioactive decay. It then cooled, but tidal heating from Jupiter could keep part of it warm. If the interior is warm enough, it could have a metallic core. A metallic core could help create magnetic effects, but the induced field does not require a strong internal dynamo. It only needs a conductive layer. The induced field is one of the best arguments for an ocean. It is also useful for estimating salinity. More salt means higher conductivity. Higher conductivity means stronger induced effects. But there are model uncertainties. The ocean could be layered. There could be different salt concentrations at different depths. Also, the ice shell could contain briny layers that conduct too, so the interpretation is not perfect. Still, most researchers agree that a liquid layer is likely. Now let's talk about the ice shell as a machine. Ice at very cold temperatures is stiff, but ice can also flow over long times. It can behave like a solid in the short term and like a very thick fluid over long time. Tidal flexing can crack the surface and make heat along cracks. Also, warm ice can rise and cold ice can sink, a process called convection. If convection happens, it can move material up and down. It can create chaos terrain. It can carry surface chemicals downward. It can also bring ocean material upward, freezing it near the surface. So the ice shell could be the main transport system. If the shell is too thick, convection might still happen if the lower ice is warm. If the shell is thin, cracks might reach the ocean. There could be both. Now think about the seafloor. If there is a rocky mantle, heat can drive reactions. On Earth, hydrothermal vents are driven by heat from magma and by chemical reactions. Europa might not have active volcanism like Io, but it could have warm rock due to tides and radioactivity. Even a modest heat flux can support hydrothermal circulation if water can circulate through porous rock. If that happens, chemicals like hydrogen could be produced. Hydrogen plus carbon dioxide can support microbes on Earth that make methane. This is called methanogenesis. If similar chemistry exists on Europa, it could support a simple biosphere. Now, how much energy is needed? Microbes can live on very low energy. On Earth, some microbes in deep sediments live with extremely slow metabolism. So Europa does not need to be a high-energy world to host life. It needs stable niches with steady gradients. If the ocean has vents, niches could exist. If not, niches might still exist in chemical gradients at the ice interface. Now we talk about the surface patterns again, because they show activity. Europa's surface has long lines that can run for hundreds or thousands of kilometers. Some are simple cracks, some are ridges, some are bands that look like spreading centers, where the ice moved apart and new material filled in. This looks like plates spreading on Earth, but in ice. If ice spreads and new ice forms, then old surface can be destroyed and replaced. This is consistent with a young surface. It also suggests that the ice shell can recycle. Recycling can bring surface chemicals into the interior. It can also bring interior material to the surface. Now, what about the color? Europa is not pure white. It has reddish-brown streaks. These colors may come from salts or sulfur compounds. Some of these could be from the ocean. Some could be from Io. Some could be from impacts. But in any case, they show chemistry beyond pure water. Chemistry beyond pure water is good for life because it provides ions and reactive compounds. Now, there is a debate about what salts are present. Some studies point to sulfate salts. Others point to chloride salts. Chloride salts are closer to Earth, like ocean salt. Sulfate salts can be present too. The exact mix affects pH and chemistry. A chloride-rich ocean could be similar to Earth's ocean. A sulfate-rich ocean could be more different, but both could still host life. Now consider the pH. If the ocean interacts with rock and produces hydrogen, it might be alkaline. If it is influenced by sulfur chemistry, it could be more acidic. Earth has life in both acidic and alkaline environments, but the energy pathways differ, so knowing the pH helps predict what metabolisms could exist. Now, the case for life also depends on where to look. If we had a plume, that would be the best place to sample. If we have no plume, then we might look for young cracks where ocean material might have reached near the surface. Chaos terrain could be good. Ridge areas could be good. Recently resurfaced areas could be good. The age of the surface can be estimated from crater counts. Fewer craters means younger. If a region is young, it is more likely to contain less processed material. Now, there is an important safety issue in real missions. If we ever send a probe into the ocean, we must avoid contaminating it with Earth microbes. That is called planetary protection. Europa is considered a place where Earth microbes might survive, so missions must be sterilized and planned with care. Now, one reason Europa is a strong target is that it is not too far. It is within reach of current spacecraft. We can get many flybys. We can build maps. We can plan follow-up missions. This makes Europa a practical path to answer the question. Now think about the big picture. If life exists on Europa, it may be separate from Earth life. It might use the same basic chemistry because the laws of chemistry are the same. It might use water because water is common and useful. It might use carbon because carbon forms many compounds. But it could still be different in details. If we found even a single alien microbe, it would change biology. It would help us understand whether life is a common outcome. Now, there is another possibility. Europa could have been seeded by life from Earth. This is called panspermia. It suggests that microbes could travel between planets on rocks thrown out by impacts. Earth has been hit by large impacts that can send rocks to space. Some of those rocks could reach other worlds. Mars rocks have reached Earth. So it is not impossible. But even if Europa was seeded, it would still show that life can survive and spread. Also, the odds of transfer to Europa are lower than to Mars, because Europa is far and inside Jupiter's gravity. So a truly independent origin is still possible. The best way to decide is to compare the biology. If it uses the same genetic code and similar core proteins, it could be related. If it is truly different, it could be independent. But that is far in the future. Now let's be honest about the limits. We do not yet have direct proof of an ocean, in the sense of seeing water directly. We have strong indirect evidence. We do not know the ice thickness well. We do not know the ocean composition well. We do not know the heat flow at the bottom. We do not know if plumes exist. We do not know if life exists. So the case is not a claim of life. It is a case that the place is worth looking. It is a case that Europa may be habitable. And in science, a habitable ocean under ice is one of the best reasons to explore. Now, let's build a clean summary of the argument. Europa likely has a global ocean under ice. That ocean is probably salty, which means it likely contains dissolved minerals. The ocean likely touches rock, which can supply chemicals and support reactions. Tidal heating provides a steady energy source. Surface radiation can create oxidants, which could add more energy if transported down. Europa's surface shows signs of activity, suggesting the ice shell moves and may exchange material with the ocean. These facts combine to make Europa one of the strongest candidates for microbial life in our solar system. With upcoming missions, we can test this step by step. The case for life on Europa is the case for a hidden ocean that has the ingredients and energy that life needs, even without sunlight. To understand how strong the case is, it helps to look at the evidence like a detective story. Each clue by itself can be argued. The power comes from how the clues support each other. Start with the surface. If Europa were a dead, frozen world, its surface would look more like Callisto, another moon of Jupiter. Callisto is covered in craters. It looks old. It has been sitting for a very long time with little change. Europa looks different. It has fewer craters, and the cracks are everywhere. This suggests the surface has been reshaped. The simplest reshaping process is ice moving, because something below is warm. That does not prove an ocean, but it points toward internal energy. Then add the magnetic evidence. The magnetometer result is a physics clue. It says there is likely a conductive layer. The best known conductive layer for an icy moon is salty liquid water. This clue is not based on images. It is based on how electromagnetism works. If you accept both clues, the picture becomes clear. There is internal energy, and there is a conductive liquid layer. That combination strongly favors an ocean. Now ask the next question. If there is an ocean, where did the salt come from? Salt does not appear by magic. It usually comes from rock. On Earth, ocean salt comes from long contact between water and rock, through rivers and through seafloor processes. On Europa, there are no rivers, but water can still leach minerals from the interior. That suggests the water has had time to interact with rock. Now move to energy again. A dark ocean needs energy in forms that chemistry can use. Heat alone helps keep the water liquid, but life needs reactions that can power metabolism. The strongest candidate is seafloor chemistry. The second candidate is oxidants made at the surface. This is where Europa becomes more than a simple ocean. It may have a top-down source of chemical power and a bottom-up source. On Earth, the deep ocean is not cut off from the surface. Oxygen and organic matter sink from above. At the same time, heat and minerals come from below. Life uses both. Europa could be similar, even if the details differ. Now, it is fair to ask how the surface and ocean could exchange material through thick ice. The answer could be a mix of slow and fast processes. Slow processes include convection in the ice. Over thousands to millions of years, warm ice can rise and cold ice can sink. If the ice contains pockets of brine, those can move too. This can bring surface material down gradually. Fast processes include cracks that cut deep. If a fracture reaches a warm layer, it can open pathways for brine to move. It can also allow water to rise part way and then freeze. Even if fractures do not reach the ocean, they can still connect the surface to deep, warm ice that has interacted with ocean water. This kind of transport is hard to prove from far away, but the patterns on the surface make it hard to ignore. Another point in the case comes from heat flow. Europa does not need huge heat flow to keep an ocean, because ice is a good insulator when it is thick enough. A small but steady heat supply can keep the base of the ice at the melting point. The key is not high temperature. The key is persistent temperature. Also, ice with salt melts at lower temperatures. If the ocean or ice shell contains salts, it can stay liquid more easily. Now consider pressure. At the bottom of a deep ocean, pressure is high. On Earth, life exists under high pressure. Pressure itself is not a barrier. It changes how proteins and membranes work, but microbes adapt. In fact, high pressure can help keep water liquid even when temperature is low. So Europan pressure is not an argument against life. Now consider the chemistry of oxygen. On Earth, oxygen is both helpful and harmful. It provides energy, but it also damages cells if not controlled. Life evolved tools to manage it. On Europa, oxidants might be present if surface products are carried down. If they are present, they could support metabolism. But the amount matters. Too much could be harsh. Too little might not matter. So a key measurement is how much oxidant could be delivered. This depends on how fast the ice cycles. Now let's talk about what Europa Clipper can measure that directly relates to life potential. One measurement is ice thickness. Thinner ice means easier exchange. Another is surface composition. Certain salts could suggest ocean material is present. Another is the heat pattern. If some regions show signs of warmth, they may be active. Another is the presence of water vapor or particles above the surface, which could hint at venting. Another is the gravity signal. If the ice shell floats on water, the way it responds to tides can be measured. Europa is flexed by Jupiter. The amount it flexes depends on whether there is a liquid layer. This is called tidal love numbers in physics. But the idea is simple. A liquid layer lets the shell move more. So gravity and shape measurements can support the ocean case and estimate shell properties. Now, if we imagine life on Europa, we should imagine it as a small set of possible lifestyles. One lifestyle is rock-powered life at the seafloor. Microbes could live in warm pores and cracks in rock. They could use hydrogen from water-rock reactions. They could use carbon dioxide dissolved in water. They could make methane and build biomass. Another lifestyle is life near vents, if vents exist. This could be more active. Another lifestyle is life near the ice-water boundary, using oxidants and other chemicals delivered from above. Another lifestyle is life in brine pockets within the ice shell. These are all microbial possibilities. Now, what about the idea of a food web? On Earth, complex life needs large energy flow. Without sunlight, complex life can still exist, but it depends on how much chemical energy is available. Deep-sea vent communities include worms and crabs, but they rely on strong vent chemistry. Europa may or may not have enough energy for large life. Many scientists think microbes are the realistic expectation, and microbes are enough. A microbe is a complete living system. Now, we should talk about the difference between life and pre-life chemistry. Even if Europa has no life, it could still have complex organic chemistry. Water plus rock plus energy can build organics. If we find organics, that is still important. It shows that the building blocks can form in oceans away from the sun. So Europa offers two discoveries. One is life, the other is complex chemistry. Now think about the history of Europa in time. Europa has likely been exposed to impacts over billions of years. Impacts can punch through ice, at least locally, and create melt pools. Impacts can deliver heat and can deliver organics. A large impact could create a temporary lake under the surface or within the ice. That could be a place where chemistry happens. If there is an ocean, impacts could also stir the surface and help mix materials. So even impacts can help the chemistry story. Now, there is a common misunderstanding about Europa. Some people imagine the ocean as a warm, open sea like Earth. It is not. It is probably cold, dark, and covered by thick ice. But the deep ocean on Earth is also cold and dark. Life does not need light. It needs energy and chemistry. So we do not need a sunny ocean to have life. Now let's talk about the kinds of measurements that would weaken the case. If Europa Clipper found that the ice shell is extremely thick everywhere and shows little sign of exchange, the surface oxidant idea would weaken. If it found the ocean is very low in salt, the conductive layer interpretation would need adjustment, though a low salt ocean could still exist. If it found very limited internal heat, that would raise questions about long-term ocean stability. But even in those cases, a rock contact ocean could still exist. Now, let's talk about why Europa is often compared to Earth's subsurface ice environments. In Antarctica, there are lakes under ice, like Lake Vostok. There are also oceans under ice shelves. Microbes exist in some of these environments. They survive with little energy. These places show that life can persist under ice. However, Earth environments still receive some nutrients from the surface and from the wider ocean system. Europa might be more isolated, so the comparison is not perfect. The point is not that Europa will be like Antarctica. The point is that ice-covered water can host life. Now, one more part of the case is that Europa is not alone. It is part of a larger family of ocean worlds. There may be many icy moons with oceans. If that is true, then the solar system might contain many habitats. Europa is the best target because it is large. It likely has rock contact, and it is accessible to study. So Europa is a gateway. It is the first strong test. If Europa is lifeless, it may still teach us how common or rare life is. If Europa has life, it suggests many ocean worlds may also have life. That is why the question is bigger than one moon. Now, let's return to the core statement. The case for life on Europa is not a promise. It is an argument that Europa has the right conditions and that those conditions can be tested with near-term missions. It is the argument that a salty ocean under active ice, warmed by tides, touching rock, is one of the most reasonable places to look for microbes. It is also an argument that even if we do not find life, we will learn how chemistry and habitability work in places far from the sun. We are close to the time when these questions move from theory to measurement. Europa has held the strongest kind of mystery, a mystery we can actually reach. To reach it with science, we have to translate big ideas into simple questions. How thick is the ice in the most active places? How salty is the ocean? Does the ocean touch rock? How much heat leaks out of the interior? What chemicals are on the surface, and which of them look like they came from below? Do we see any signs of gas or particles leaving the surface? These questions are not poetry, they are measurements, and each measurement changes the probability of life. Now, let's look at the possibility that the ice shell is layered. On Earth, sea ice can trap brine in channels. Over time, those channels can drain or refreeze. In thick ice, you can also have pockets of liquid water trapped between layers. On Europa, the pressure and temperature conditions could allow brine layers within the ice shell. If there are brines, they can act as a temporary home for chemistry. They can also act as stepping stones for material exchange. Imagine oxidants formed near the surface. They might not need to travel all the way to the deep ocean right away. They could move into a brine layer. Then over time, convection or cracking could move that brine deeper. This kind of staged transport could allow chemicals to survive and move. It also means that life, if it exists, might not be only at the seafloor. It could be in brine layers where chemistry is active. Now consider that Europa is constantly being flexed. Flexing creates stress. Stress creates cracks. Some cracks may open and close with the tidal cycle. That can pump material. It can also grind ice and make heat along crack walls. In some models, this can create local warm zones. If warm zones exist, they could be places where liquid water is closer to the surface. Again, this increases the chance of exchange. Now there is a question about whether Europa has enough phosphorus. Phosphorus is important for life on Earth. It is part of DNA and cell membranes. In oceans, phosphorus often comes from rock, but it can be locked in minerals. If European rock chemistry releases phosphorus into the water, it can support life. We do not know this yet, but we can look for hints in the kinds of salts and minerals that appear on the surface. Future missions may also detect certain elements directly. Now consider the role of sulfur. Europa may receive sulfur from Io. Io puts sulfur and oxygen into Jupiter's space environment. Those ions can hit Europa and become part of the surface chemistry. Sulfur can be used by some microbes as part of energy reactions. On Earth, many microbes use sulfur compounds, so sulfur on Europa could help, depending on transport and concentration. Now consider the idea of a redox balance. Redox means oxidation and reduction. Life often works by moving electrons from a reduced chemical to an oxidized chemical. If Europa has oxidants from the surface and reduced chemicals from the seafloor, it has a redox engine. The amount of power depends on how much of each is available. If the ocean is strongly reduced and has little oxidant, life could still exist, but it might be limited to seafloor zones. If the ocean receives oxidants from above, life could spread more. So the exchange question is central. Now, let's talk about what it would mean to find a biosignature in a plume. A plume sample might show water, salts, and organics. But to argue for life, we would want more. We would want to see patterns that fit metabolism. For example, a certain ratio of methane to carbon dioxide might be hard to keep by geology alone, or certain amino acids might appear in a strong pattern, or certain complex molecules might appear in a mix that is unlikely from random chemistry. But a key point is that we would need multiple independent clues. Science tends to be cautious with life claims for good reasons. Now imagine that we do not have a plume and we land instead. A lander could analyze ice grains. It could melt a small sample. It could look for organics. It could look for salts. It could look for specific chemical gradients. Even on the surface, you might detect oxidants that are products of radiation. That would help us estimate how much chemical power exists at the top. A lander could also measure the local radiation environment and how quickly organics are destroyed. That would help interpret surface chemistry. Now, there is also an argument based on how common ocean worlds may be. If we count the likely oceans in the solar system, we get a surprising list. Europa, Enceladus, Titan, Ganymede, Callisto, possibly Triton, and maybe more. If many worlds have oceans, then oceans might be a common outcome. If oceans are common, then habitability may be common. And if habitability is common, then life might also be common. But we do not know. We need a test. Europa is one of the cleanest tests because we have strong evidence for water and energy. Now, one more question is whether Europa has enough internal mixing. If the ocean is trapped under ice for billions of years with little mixing, chemicals could become evenly spread and reactions could slow. But tides can drive mixing. Heat differences can drive circulation. If the seafloor has vents, that can also drive circulation. So mixing is plausible. In fact, tidal forces could drive strong currents under the ice. These currents could move nutrients. They could also move heat. So the ocean might be active, not still. Now think about what makes a microbe survive. A microbe needs a source of energy, a source of carbon, a source of nitrogen, and a set of minerals. It also needs stable water. Europa likely provides water. Energy could come from hydrogen and other reduced chemicals from rock. Carbon could come from dissolved carbon dioxide, carbonates, or organics delivered by impacts. Nitrogen is less certain, but it could exist in ammonia or other forms. Minerals could come from rock, so the inventory is possible. Now, take a step further. If life exists, it will change its environment. Even microbes can change chemistry. They can consume certain chemicals and produce others. Over long time, this can create measurable signatures. So if Europa has had life for a long time, it might leave a chemical fingerprint in the ocean or in materials that reach the surface. That is another reason why long time matters. Now we should also consider that Europa might have multiple ocean layers. Some models suggest the ocean could be divided by high-pressure ice phases at depth. High-pressure ice is ice that forms under high pressure and can be denser than water. If such layers exist, they could separate the ocean from the rocky mantle. If the water does not touch rock, the seafloor chemistry argument weakens. But many models still favor rock contact, especially if the ocean is not extremely deep. This is an area where better gravity and magnetic data can help. Europa Clipper is built to improve these constraints. Now, there is a final part of the case that is more practical. Europa is interesting because the question is answerable. We can measure the ocean. We can map the ice. We can sample material. We can plan. This is not like faraway exoplanets where we only see a point of light. Europa is a nearby laboratory. It is a world where habitability is not an abstract idea. It is a set of measurements and a set of planned missions. And it is a chance to learn if the universe has more than one living ocean. One last way to frame the case is to ask what would make Europa unfit for life. If there were no ocean, the story would end. But the evidence for a liquid layer is strong. If the ocean were completely cut off from rock, the energy and nutrient supply would be weaker. But interior models suggest rock is there, and contact is likely. If the ocean chemistry were missing key elements, life could struggle. But impacts and rock contact can provide many elements, and the surface chemistry hints that Europa is not chemically simple. If the ocean were short-lived, life would have less time to start. But tidal heating and orbital resonances suggest a long-lived system is possible. If the ice shell never allowed exchange, oxidants from the surface would not help. But the surface features show a shell that is not quiet. So the case is not that everything is perfect. The case is that none of the obvious deal breakers are clearly present, and several strong positive signs are present. That is why Europa stays near the top of the list. It is also why scientists talk about Europa in terms of probabilities. We do not have certainty. We have a set of reasons that push the odds upward, and the next stage is to stop guessing. We will map the shell. We will measure the ocean. We will study the chemistry. We will watch for venting. We will choose the best places to sample. Over time, the question will narrow. If the best data shows strong energy sources and strong exchange, then the case for microbes becomes stronger. If the best data shows weak energy and weak exchange, the case becomes weaker. Either way, the answer becomes clearer. And if we ever do sample European water directly, either through a plume or through drilling, then the question becomes direct. Are there cells? Are there complex organic patterns that match living processes? Are there unmistakable signs of metabolism? That is the long arc. For now, the case for life on Europa is the case for a hidden ocean that behaves like a real world, not just an idea. An ocean with tides, an ocean with chemistry, an ocean with a surface that keeps breaking and reforming. A cold, dark ocean does not sound inviting, but nature does not care about comfort. It cares about energy and chemistry. Europa may have both. There is also a human reason Europa matters. It is a reminder that the solar system is not only planets, the moons are worlds too. For a long time, the search for life focused on Mars. Mars is a desert today, but it once had rivers and lakes. It is close, and it is familiar. Europa is different. It does not offer a dry landscape to walk on. It offers an ocean we cannot see. It offers a place where the signs are indirect. And yet, the science case is strong enough that we are sending a major mission. That tells you something about how the evidence has changed. We used to think that a place had to be warm and sunny to be alive. Now we know that life on Earth can live without sunlight. We used to think that oceans could only exist on planets. Now we see that moons can hold oceans too. We used to think of ice as a dead barrier. Now we see that ice can be active, moving, cracking, and cycling. Europa collects these lessons in one target. It is not an easy target, but it is a clear one. It is also a target that forces us to be precise. We cannot say life is there just because we want it to be. We have to measure the ocean, measure the shell, and measure the chemistry. The case is strong because it can be tested. And when a scientific case can be tested, it stops being a story and becomes a real question with a real path to an answer. In the years ahead, we will learn if Europa's ocean is deep or shallow, if its water is rich in salts, and if its ice shell is mostly a sealed lid or a living, shifting skin. We will learn which surface areas are young, which ones are old, and which ones show the clearest signs of materials that came from below. We will learn if there are occasional bursts of water vapor, and if those bursts carry salts and organics. We will learn if the moon gives off more heat in certain zones, a hint of active processes inside. Each measurement is a step from possibility to constraint, and in the background of all of it is the simple fact that a world can be cold and still be wet, can be dark and still be active, can be far from the sun and still be chemically alive. Europa is that kind of world. If you strip away the drama and keep only the logic, the case is straightforward. Europa has water in the form of ice at the surface. Multiple lines of evidence suggest there is liquid water below. The moon's orbit supplies steady tidal energy. The surface shows signs of motion and renewal. The chemistry is not just pure water, but includes salts and altered compounds. Rock is likely present beneath the water, making water-rock reactions possible. These are the ingredients that keep showing up whenever we find habitats on Earth. So the case for life on Europa is not a wild leap. It is a reasonable next question. Not, is Europa magical? But, is Europa workable? And in science, a workable environment is enough to justify the search. Somewhere under Europa's ice, if the models are right, water presses against ice from below, shifting slowly with tides that never stop. If rock sits beneath that water, chemistry can run for a very long time, making simple fuels, building new compounds, and setting up tiny gradients that microbes could use. If exchange happens, even slowly, the surface can feed the ocean with new reactive chemicals. If exchange is rare, the seafloor can still provide a steady base. Either way, Europa remains one of the clearest places to ask the oldest question, in a form that can be tested. Is there life in the dark ocean? We do not know yet, but we know what to measure, and we know how to build the missions that can measure it. Europa is close enough that the question is no longer only imagination. It is engineering, patience, and data. And that is why Europa has become one of the most serious targets in the search for life. In the end, the case is built on a simple idea. Where there is liquid water, chemistry, and energy, nature has a chance to do more than geology. Europa appears to offer those conditions in a stable, planet-sized ocean hidden under ice. That possibility is worth the long trip and the long work. And if the answer is no, that matters too. It would tell us that water and energy are not enough by themselves, and that life may need rarer steps. Either way, Europa will teach us something basic about the universe. For now, the best we can do is follow the evidence, build the tools, and keep asking the question in ways that measurements can answer. Then, step by step, we will learn what is true in the years ahead and beyond. The search continues. This was a quiet archive story, where the story ends, sleep begins,